My name is Henrik Zetterberg. I'm a professor of neurochemistry at University of Gothenburg and at University College London. My specialty is fluid biomarkers for Alzheimer's disease and other neurodegenerative dementias. This question about whether or not to use ratios for biomarkers, to me it's a hot topic, and I have a little bit of a strong view on this, which is not completely accurate, I think. But as a clinical chemist, working as a physician in a clinical lab, I like to look at each biomarker measure by itself when I look at results from patient samples. So I start by looking at amyloid. Is it positive or negative? High or low? And low is then indicating amyloid pathology in the brain. Then I go to the tau molecules and look at total tau and phospho-tau to determine if there is a neuronal reaction to the pathology and how intense that reaction seems to be. But that's one way of looking at the data. If you look at group level data where you want to maximize your ability to distinguish Alzheimer patients from patients with other diseases or patients who do not have neurodegenerative disease, then the most information-rich measure is a tau a beta ratio. You can see that quite clearly, that separates the groups the most efficiently and with the highest sensitivity and specificity. But I'm still a little bit afraid of just using that. So my advice is often to look at both the individual biomarkers and the ratios. But if you would need to pinpoint one single measure with which you maximize your chances of diagnosing your patient correctly, then it is this ratio, tau divided by A beta. One could also make it a little bit more specific and state that phospho-tau divided by A beta 42 might be the best ratio that gives you the least overlap across groups, fewer gray zone results, and a more clear patient outcome in terms of biomarker-based diagnostics. I think the explanation for why it is like this is that this biomarker ratio captures two aspects of the same pathological process in the brain. So we have amyloid aggregation, which is reflected by A beta 42, and then we have tau, which then marks the amyloid-induced secretion of tau from neurons affected by the pathology. So we have, I both like and dislike the ratio, I have to tell you. I will explain why very shortly. It captures two important processes in the same ratio in Alzheimer's disease. And that's a really good thing, and that's why I like it. Why I don't like it is that I am also a clinical chemist, and I'm used to using biomarkers that a biomarker to me is something that really reflects one biological process. So I think mixing two processes like this in a ratio takes away a little bit of the information, but that is perhaps a bit old-fashioned also. So from a patient perspective, and if you are working as a clinician, perhaps the ratio gives you the maximum information, and looking at each individual biomarker by itself, perhaps that's just me as a lab physician who wants to do that. But I would like to know how much amyloid aggregation there is and look at A beta separately, and then how much neuronal response or neuronal impairment by amyloid there is, and then look just at total tau and phospho-tau also. But it's a good question. It's I think maximum information, if one just had one figure to look at, then I would prefer the tau A beta 42 ratio. Now we are talking about the biomarker history of a little bit longer than 20 years. So it became clear quite rapidly that amyloid plaques are composed of beta amyloid, and that there was a particular form of beta amyloid which is quite sticky. That's the 42 amino acid long beta amyloid form. All of us make it, but we also make shorter forms, A beta 40, 38, 39. These shorter forms are more water soluble. But A beta 42 has a strong tendency to stick to itself and to stick to lipids and to clump together. And that is what's happening in amyloid plaques in the brain. It's not entirely clear why some will get this early and some won't, but ApoE genotype plays a big role. When the process starts, CSF beta 42 concentration goes down because the molecule can't stay in solution. It ends up to a larger extent in the brain tissue, making these plaques grow. So that is CSF beta 42. A reduction indicates retention of the peptide in the brain parenchyma. One could also call it a defective clearance of the protein from the brain parenchyma to the fluids. Instead, you get another clearance pathway, which is then into the plaques. When plaques form, it has become clear that surrounding synapses and neurons, they will get a direct or potentially via microglia and astrocytes a signal that they should prune. One should remove synapses close to the plaques. And I think this is a physiological pruning mechanism. This is very speculative, by the way, but I think beta amyloid plays a biological role when you prune synaptic networks physiologically. But I think this is then a constant pruning signal, and then what happens is that you phosphorylate tau, the neurons phosphorylate tau, and then tau lets go of the microtubuli. The axons can start to degrade. The neuron will still be alive, but it will have to handle a lot of mobilized tau from the microtubuli. And that tau is secreted and degraded in the lysosome. So secretion of tau will, both phosphotau and total tau, will lead to higher CSF levels of total tau and phosphotau. So in short, amyloid in CSF marks onset of amyloid pathology and aggregation, and total tau and phosphotau mark the neuronal response to the pathology.